Hello everyone, we are presenting Admission Controller for Kubernetes under Anvil. My name is Yuhan Huang, and my teammate is Frederick Chu and AJ Grama. We will walk through why admission controllers matter and how Anvil help us formally verify them and the details of our implementation. Before introducing our work, we should have a brief introduction about Anvil, which our work based on. Since real-world Kubernetes controllers often encounter hundreds of bugs due to asynchrony issues, Anvil is a framework to verify the controller and focus on reconciliation logic. Anvil has been demonstrated on controllers like Zookeeper, RabbitMQ, and FluentBit. And Anvil introduced a concept of ESR. ESR is an abbreviation of eventually stable reconciliation and defined as if the desired state is always X, then eventually the cluster state matches X and always matches X afterward. Make sure the cluster eventually reach desired state and won't be crashed or stopped according to a synchrony issue. What is Kubernetes and why is admission control important? Kubernetes is the industry standard platform for running containerized application at scale. It automated deploying, scaling, and managing application across clusters of machines. Admission controller are critical gateway in Kubernetes. They check every request to create or modify resources. More importantly, it will reject any invalid or unsafe requests and maintain reliability, security, and consistency of the cluster. Why is validity as important as ESR? If the input, the desired state, is already invalid, reconciliation will eventually redirect current state into wrong state, which also cause security issues and waste of resources. If the goal is already wrong, we will never get the correct answer. Our work focuses on three built-in Kubernetes controllers. The first one is replica set. It can be seen as a part of a deployment, just as this picture shown. The second one is deployment. It is like a upper version of replica set. Deployment manages a set of pods to run an application workload, usually one that doesn't maintain state for work, like continuous delivery, continuous deployment workflows, and web front end. The third one is stateful set. It is also run as a group of pods. What what's made it different from deployment is that each pod get their own identity and used for managing applications that need persistent storage or a stable unique network identity. It often used on database like MySQL and PostgreSQL.
So now we are going to go over the main procedure of building and verifying our three different admission controllers at a higher level. The first step of the process is designing a spec for our three different controllers. This required us to use Varus and Rust code to specify what were and were not valid inputs to their respective controllers. This process required us to pretty rigorously examine Kubernetes documentation and even perform some of our own testing to verify more ambiguous cases of what was and wasn't valid. One example that came up a lot is that most time-based specifications in Kubernetes documentation did not explicitly say what was and was not valid, but it quickly became clear through testing that these fields would not accept negative values. A lot of different tests like this made for a pretty rigorous specification on our end. But in our case, most of these specs involved checking if a field is present or checking that values of fields lie within certain bounds, usually that they're non-negative or that they're positive or that they are less than some other field. And these were all written as open spec functions in Varus. After defining the properties that we want to hold in our controllers, we can design the executable version of it. This means that we create an executable version of the specification mentioned before, but we also create all of the underlying infrastructure for our Kubernetes controller. In the case of our admission controllers, they were run as an admission webhook server in kubeRS, which allowed for easy testing using various manifests. But this also required us to set up HTTPS with TLS certificates in order for it to get the controller up and running properly. This server accepts configurations based on each controller's respective fields and validates them. And for each controller, we had to ensure that they ran correctly. So in order to do this, we created a testing suite for each one that feeds several different manifests into the admission controller and tests if the acceptance or rejection behaved as expected. These manifests were essentially just really big YAML files of configurations for the controller just to see if every single field behaved properly. And finally, we end at the verification step, which is also done using Varus. To get this verification to work, we must first provide Varus with a formal model of the Kubernetes objects that we use. This is essentially just a big struct that contains all the values expected by that field of the specification. This must be done because Varus does not know the ins and outs of the object that we're using. Varus solves the correctness of programs. It doesn't necessarily know the ins and outs of deployment software like Kubernetes. These structs, or views, allow Varus to easily reason about their behavior while maintaining a link between the executable controller and its specification. And then to complete the proof, we must show that the executable version matches up with the specification in terms of its expected behavior. And this is actually written as a post condition in our executable code. That's meant to be verified by Varus. And in order to satisfy this condition, we can employ techniques from various like pre and post conditions, assertions, and invariants to verify the intermediate expressions leading up to the overall proof predicate. Using Varus also provides us with the benefit of knowing which statements were unproven, allowing us to easily know where we went wrong and proceed further.
So here we have some nitty-gritty details of the proof process for each admission controller. Admission for a replica set is the first one we try to prove, and a lot of the details have already been filled in by the Anvil team. For example, selector should match template labels, but they already implemented a match function for selector, so we didn't have to prove that. The proof for replica set is pretty straightforward. After checking that replicas are not negative, we just had to make sure that fields for template and selector exist and template matches selector. This only took us 8 test cases to check every possible code path. For deployment, it actually isn't too far away from replica set, only introducing 4 new fields, 2 of which have completely no restrictions. For example, one of the new field is strategy, and it has to either be rolling update or recreate. However, it did prove to be a little bit more tricky since some field's constraint depends on another field, and that field might be optional. So min-ready seconds here should always be smaller than progress deadline seconds, but progress deadline seconds might not exist. So does that mean min-ready seconds can be as large as it wants? The answer is no. It still has to be smaller than the default value of progress deadline seconds, which is 600. So the proof requires some careful maneuvering of the spec and execution code. Stateful set was the hardest one, as it not only have a lot of similar fields as deployment, so like all the usual non-negative stuff, but it also has a volume claim templates field. This is an array of a non-primitive type, and non-primitive types are a lot harder to reason about. Since they are not supported directly by Varus, we had to create view types for these. It also required much more advanced proof techniques such as loop invariants, assertions, and introducing ghost variables. So to wrap things up, our core contribution was the successful creation of 3 distinct admission controllers that weren't just functional, but also formally verified. This required careful designs of specifications, admission code, and proofs. A key enabler in this process was the Anvil framework. It provided us the necessary abstractions to model and prove the specifications. Varus was also crucial in the refinement of our controllers. Thanks to Varus, we found multiple issues in our implementation or specification during the process whenever Varus didn't agree with our implementation. With powerful tools like Anvil and Varus, we can prove critical components like admission controllers and achieve correctness and reliability in today's systems. Finally, we would like to extend our special thanks to the Anvil team and Shudong Sun, as their guidance and insights were invaluable throughout the entire project. That's all we have today. Thank you for your time and attention.